All right. So today, welcome back, Precalcers. We are looking at 1.2 and we are graphing equations. So right off the bat, how many of you think you remember how to graph basic stuff, like Algebra 1 basic stuff? Do you want this in your notes or you just want to go do them up at the boards right now? Okay, we'll do boards, but you can take your notes up to the board. I know that not everybody loves that. We'll switch back and forth between how much we move up there. But your job right now, I want you guys to go up to the boards and you are going to graph with table. Okay, and we're not going to get any crazy graphs right now. This will be a couple minutes up there. But I just want you guys to graph me, we'll say 2 equations. And we'll just jump right in. Okay, the first one that you're going to make a table and graph is the equation y equals 2x plus 3. And the second one that you're going to graph by making a small table for me is y equals x squared minus 1. Now, I'm going to be honest. I care way more about the table that you make than I do about the graph itself because I think you can all plot points. So really, I care. As long as you get the table, I'm cool with it. We'll look at the graphs together. But in the groups that you're in, I want you to find a blank board, and I want you guys to go make me the tables that would produce the graphs of those. Checking these out. Liked what I'm seeing. Some groups did more work than necessary, but as we look at these, just to make the table, and I'm not going to show both of them necessarily, what I really, really, really like about, let's see, some group did it wonderfully. If we look over here, where I think it was Hawaii and Lily were working, if we look at their table for the second one on B, what's different about their table compared to everybody else's on B? So they have a parabola, but I think everybody does. So they went to the negatives, but so did this group up here. They just had -1 and -2. What's right in the middle of their table? That lowest, the 0, the vertex, right in the middle of their table, and it works out nicely. But just as a quick recall, if you guys want some in your notes, as long as we're doing this, I'm going to identify a couple little things. Can you guys, I know that we see it up on the board because we just did these, but what kind of graph is this going to be? That's a line. It's on part A, it's just a line. How many points do we actually need for a line? We need 3 points for a line? 2 points is all we really require. 2 points needed. Now, it doesn't really matter what they are, right? Everybody's going to pick a pretty easy one, I imagine. And just to fit on the screen, this is going to be super annoying. I'm going to do my table sideways. Just for the first one. What's the easiest x value you can possibly pick? 0. And then we get 2 times 0 is 0 plus 3 is 3. Okay. What we have just identified, and we're going to talk this out, so make sure your ears are wide open, is that x value and that y value show up on the graph together. So if we think about the graph as being just a way to visualize all of the answers to some particular equation, this is one of the answers that we're going to see. A solution point. This makes the equation true. Any point that we put up here should make that equation true as long as we're not doing things goofy. Give me another x value to use. Sure, 1's a good choice. When I plug that in, I get 2 times 1 is 2 plus 3, 5. How many solution points do we have on the board right now? 2. Now, we have 2 of the infinitely many that exist for this equation. When you put all infinitely many of these solution points together, it forms a what again? A line. A linear function is cool, but a line is all I'm looking for. Okay, from memory, on B, what does a graph of this one look like? It's a parabola. Now, for these ones, how many points do we need, really? So there's 3 points that we truly need, but that gives us 5 total values in the end because of the way our symmetry works. But we need at least 3 points. I'm going to use PTS. And then this table I will make vertical just because I want to really highlight how Naomi and Camille and Cheska and Michaela made their table. When we're doing this, you guys, I think most of you, it looks like, use the 3-column tables, which I'm cool with. We will be using our calculators to help us with tables quite a bit in here, just so you guys know, because that should be a time-saving thing. Okay, we probably don't all remember how to find the vertex right in the middle of this, and that's okay. It will not always be this way, but in this case, it's at 0. What I really like is how we had several groups do this. Now, whether you show the next line of work, I don't really care. If you can do this mental math without making a mistake, I'm good with it. 0 squared, just to make sure, I think you're confusing it with 2 to the 0. Those of you who kept asking, is it 1? If you have 0 objects and you take 0 groups of them, how many objects do you have? 0. It's 0. So this 0 minus 1, which gives me what? Negative 1. Okay, if I pick another point bigger than that, 1, this is just 1 squared minus 1. What is that going to give me? 0. Now, I'm going to make a claim that I have another point that I don't even need to think about. That's also 0. It's going to have to be. We have symmetry. I'm thinking a bit ahead. If you just guess and hope that works, be careful. But these 3 points will get us a parabola to graph. Okay, do we need to talk about plotting these points? Are we cool with it? Okay, so when we're talking about graphs of equations, we just kind of started with, hey, show me that you still remember how to do this, and everybody seemingly does, which is awesome. But one of the reasons that we care so much about these graphs is because we get a ton of information out of these guys. So we're just going to talk a little bit more. We're obviously still on the graphs, but let's talk about some key features. And there will be more than we necessarily list right now, but we certainly need to lock in and agree on what's important to look at on a graph. Okay, when we are given a graph or an equation that we're asked to graph, there's a few things. We obviously have the graph in front of us. I might ask you about what x values can I use in this function. Does anybody remember what it is I'm talking about? What x values can I plug into this? Ooh, somebody said it, I think. It's the domain. I might ask you for the domain of a function. Now, we're not going to hit the domain hardcore right now, but they're not crazy hard. In our worlds, there's only a few small situations where the domain gets goofed up. What can't we divide by? So any x that makes the denominator 0 is not in the domain. You would have to get rid of it. Any other things that we can't do? Like square roots is what come to my mind. Can't divide by 0, there's 1. What can't I take the square root of? Nicely. A negative. So if there's a square root and an x in the problem, we probably have to worry about the domain a little bit. There's some other places. Logs have some special rules that they do that we probably don't remember. The trig functions have some special rules that you may or may not remember. But we will be dealing with those. We'll work up there. I might ask you about the domain, which means I might ask you about the what? Range. What is the range? It's the set of all the y values or the outputs of my function. So we'll certainly talk about domain and range stuff. On the graph itself, are there any places on the graph that I might, or we might rather, look at a little closer than other points? Any special places on a graph? Like if I draw this graph, and you don't have to sketch, it's just a random graph. Let's do a wonky one here. Okay, you guys hoot and holler when I'm at a point that you might consider an important one, and I'll make it bold so you can see where I'm at. Right here, what did you just identify? You found a minimum. Okay, I agree, that might be an important part. Okay, I'll keep going. What is this? Okay, I heard like 5 people talk with different words. The y-intercept. Okay, any others? There, what's this? Hey, because we're going to spend such a crazy amount of time on these, we better talk a little bit about intercepts. Do I need to define it? Where's the x-intercept? It's where the graph crosses or intersects the what? The x-axis. Do we have to write that down? Okay. Algebra 1, you probably would, but here we are. We have the intercepts. Okay. I'm going to close that because Russell's loud and has gym this hour. All right. Our intercepts come in 2 flavors. What's one of them? The x-intercept. So we're going to sketch a graph between these, and it's not going to be super specific, but I agree, the x-intercepts. So let's look at those as one little subsection. X-intercept. Now, I'm going to go ahead and say intercepts like that, just in case there's more than one. In simplest language, this is where a graph does what, Chetty? Love that you said touch instead of cross, because it could just touch and turn around. Okay, the x-intercepts, they just touch the x-axis. Okay, in contrast with that, we also are going to have some y-intercepts, and we're going to make, or we're going to rephrase that. We have y-intercept that we might be after. Now, I'm going to draw a small graph underneath, and what's weird about the section that we're in currently is maybe, just maybe, they're not all functions. And in fact, we're going to end this section right now by graphing circles here in a few minutes, which are not functions, but we'll be able to deal with them. We have x and y intercepts. So if we think about a little graph right here, and it doesn't have to be perfect. Mine definitely won't be because I'm trying to learn this still. Let's say it's there. What? I don't like it. Sorry, you guys are just going to have to bear with me while I learn to use a new program. My other one, they said it wasn't safe to use due to vulnerabilities or something, but I can move that one. All right. So here I have this lovely thing. What is this axis right here? Horizontal? That's the x-axis. And this one is y. And it does not have to be perfect, guys, just so you know. It can be, but it doesn't have to be. If you want straight edges and stuff, I keep them up in this box this year. So you're welcome to grab one, take it, whatever you do you. As we're looking at these, I'm going to draw a graph, and it's going to be kind of squiggly just so I can get a couple of these. Boom, boom. We'll just do that one. Now, I'm going to call this thing F, just so we have a name for it. So we have some x-intercepts. We're going to talk about y-intercepts. And as we look at this graph, how many x-intercepts? I see 3 x-intercepts. Now, when we're talking about these, if I assume that we can identify them, they're here, here, and I'll put it on the board in case somebody's looking, but there's 3 x-intercepts. Now, at each of these points, I'm just going to give us an x value. And you guys are going to help me make a realization, and nothing new should come out of this. Let's say this is the ordered pair, and I'm going to draw some arrows down to them here in a second. But that looks like a comma something. If I call this as a, that's the x value, then what's the other part of that ordered pair? 0. Okay, let's say that this one happens at b, some x value over here. It's a negative. Give me another x-intercept. So I heard 0. What do you mean by 0? What's the 0 in that? Like, let me rephrase that because I think that could be a weird question. What's the ordered pair right here at b? It's b, comma 0. It could be -1, Keen, if that was the scale, for sure. Okay, last one then. Or just go out on a limb and say it's c. What should this ordered pair be? C, comma 0. Now, the reason I'm stressing this so much is there are some synonyms that we use. I might ask you for an x-intercept. If I do, I'm asking you very specifically for an ordered pair, just so you know. But there's other words that we might use. Do you remember any of them? The zeros is the one that I'm trying to make sure that you recall right now. Don't forget, x-intercepts could be zeros. Now, with or without the second E, just so you know for the spelling. It can have either. It can Z-E-R-O-S or O-E-S. I like O-E-S. It feels more natural. What's up? So fat. I thought that's an Oreo. Oh, I see what you're saying. Okay. Fair. Okay. That derailed me. What I really want to notice, in each of these, what is the y value? 0. And the reason I'm stressing that so much is because you're going to be asked to find the x-intercepts. And if you want to go through the process of making a graph and then blindly trusting your graph, you can. What if I just asked you to find these without graphing it? What would you set equal to 0? To find, and we're underneath the x-intercepts, all we have to do is let, what did you say, Lily? Or Hawaii? Or Naomi? I don't know who said it over here. And okay, well, I missed. Somebody said it in a word that sounded like the answer. That's okay. What is the y value in every single one of these? So what do you think we're going to let y equal? Boom. To find the x-intercepts, let y equal 0 and solve it. That's it. Okay. Every single time. This is how we do it. This is how we find our solutions, our zeros, our roots, our x-intercepts. What about for the y-intercept? How many y-intercepts do you count? 1. In fact, there should only be 1 if it's a function. If there's ever more than 1, then we do not have a function in front of us. But I think it's right here. If I say that that is at, I don't know, we'll say E, what's the y-intercept at? 0, comma, E. And E is a poor choice in hindsight, but that's okay. It's just a constant here. Now, these ones are nicer. It is so much easier to find the y-intercept of a graph than the x-intercepts most of the time, unless you are just able to factor everything in your head instantly. If you wanted to find a y-intercept without having to graph a big picture like this, how do you find it? What is x if we're at the y-intercept? Yeah, all we have to do is let x equal 0 and solve. Okay, so right off the bat, we're just going to check, and I know we did a little bit of this the other day. I'm okay with just table work for now, but you guys are going to use these ideas, and we're going to see how much we remember or how hard we need to hit it. So checking it out, example, bless you, find intercepts. Now, if I don't specify x-intercept or y-intercept, I want the implication to be it's both of them. Cool. And let's see here. We want a really ugly one? Okay. Here we go with your groups. And if you need to stand up and talk with another group after you have tried with your neighbors, I'm cool with it. I want you guys to do this for the following equation. Y equals x cubed minus 9x. I want you to find me the intercepts of this wonderful function. I'm going to pause it. I'm going to give you guys some time. Talk it out. I want to hear you guys discussing things. Should be working. Do we all agree the y-intercept is easier? To find a y-intercept, we just let x equal 0, right? And solve. When I do this, what do I get for y? 0. So what did I get for x and y? I got 0 for both of them. I think 0, 0 is my y-intercept here. It happens to be at the origin. Okay, cool thing is we also just found one of the x-intercepts because it is 0 here. Okay, this one's a little bit harder. I heard somebody say add 9x. Don't do it. Don't do it. It's been a while. We spent a lot of time last year, and we'll spend time this year, not as much. But if I want to solve this, what the F do I do? We factor. What's the GCF? That's where we always start. X. What does it leave behind? Okay. Cooking. Now, does this factor any further? No, but it's going to come along for the ride. We're not going to forget it. What about this inside here? How many terms? 2, which means it's a... So you all went to the right spot, just so you know. It's a binomial. It's a difference. And do I know the square root of both of them? What's the shortcut for the difference of two squares? Square root is x, and the square root is... So I always do minus first, I think. No reason to that. What's the other factor? Plus 3. Now, again, we will be going over the factoring stuff again, but it's going to go much quicker. Even if you didn't remember it, does this feel super familiar to you? Okay, so this last part, if this is true and the product of these three things is 0, then what value of x makes this equal to 0? And that's always a weird one. So we got x equals 0. What value of x makes this factor 0? 3, and the other one? Negative 3. Okay, now I've given you the solutions at this point, right? Because we just have x equals something. What did I actually ask for, though? Good, the intercept, or the points. So at each of these points, what do I know the y value is? 0, because that's what it means to be an x-axis, or x-intercept, I'm sorry, which means our x is at 0, 0. Give me another one. 3, 0. And negative 3, 0. And now we have all of our roots, our solutions, our x-intercepts. Factoring is not going to be our focus today. It's just nice to see it kind of introduced early on. Feel okay with this problem? Is this easier than graphing it and then trying to check your graph and seeing if it's right? So much easier, so much more trustworthy than that. Awesome. Okay. How much do you remember about doing circles? Just radius. Okay. Well, we may not get to circles today, but I will give you guys a little bit of time to get through a little bit of homework, but we're not starting it yet. We got one more thing we're going to look at first. Then we'll start tomorrow with circles. Okay. The second, or I guess second to last thing we're going to look at today is when we're looking at our graphs, we can find the intercepts, sure. And we've even discussed it that, like, hey, maybe we're going to wind up looking for the mins and maxes, the domains and ranges. We will get to all that stuff, I assure you. but one of the most valuable things that we have in our arsenal to graphing stuff, we use it with quadratics constantly, is the existence of symmetry. We get some graphs that wind up being symmetric. Now, if they're functions, they won't be symmetric over the x-axis, but we're only dealing with the graphs of equations right now. So, last little part for today, it'll be the last, that is way too bold. Last topic for today, then we're about to finish that chapter, or that section rather, is we're going to look at symmetry. Now, because we are not looking, yeah, I know it's annoying if you're looking at the S, but because we're not looking at functions, we're just worried about the symmetry with graphs that is possible. And because we're not dealing with functions, we get 3 flavors, or 3 different types. So there's only 3 of them that we have to worry about this, 3 types. Can anybody recall one type of symmetry that we have? So asymmetry would be a lack of symmetry, but I like where your head's at. Linear symmetry, I'm going to give us the first one. I could have x-axis symmetry. Hey, there's a second one. We have x-axis symmetry. We could have y-axis symmetry, or not vertex, but I like, we're closer to it. Origin. Okay. When we're checking for symmetry, we're going to relate this to an idea later in the chapter when we see functions and stuff. But for now, we're just looking at graphs and symmetry. And these are the graphical ways to think about it. If I want something that has x-axis symmetry, let me undo that. And I'm going to get my lovely scale again. Decided I kind of hate this. All right. So check it out. If I want something with x-axis symmetry, and we'll do one that looks kind of realistic, that's not what it's supposed to be doing. There we go. Okay, we'll pick a different color, I suppose. Boom. Okay, let's say I have this awesome graph that's coming up here, and I'm going to have some x-axis symmetry. And on this graph, I happen to have this point, x, comma, y. Now, I haven't drawn a graph that's symmetric yet. I've only drawn half of it. If we wanted this to have x-axis symmetry, this whole curve will just simply fold down under that line. Now, I want you guys to sketch it roughly on your page. I'm going to give you like a 5-second heads up. Reflect that over the x-axis. And I'm going to draw one as well. Let's just see if we get the same shape. I'm going to do it as a dashed line. Here's what I think it looks like if we reflect this over the x-axis. Now, here's the part about this that we're going to really lean into. Do we all agree that that looks like it's symmetric about the x-axis? Can you tell me with confidence any point on that graph? Like, I think I know what this point is. So I heard negative x and I heard negative y. I've heard all 4 variations of this. It's still x, right? But what happened? Negative y. We get the same values, just one of them happened to switch negative, and it's the y value because it swapped. Now, what this means is that if we didn't want to have to look at a graph, maybe, just maybe, I could replace y with negative y, and they would spit out the same x value. They should. In fact, that's exactly what would happen. And we'll make that jotted down here. What about on this one? What if I wanted y-axis symmetry? Can you think of a graph, Cheska, that has y-axis symmetry? A parabola. Love it. So check it out. We are going to draw a graph, and I'm going to try to do it a little better than that because that was not good. Z. We're going to do a graph that has a little bit of y-axis symmetry. So let's say we have this lovely point here on it. If I plug in, I'm going to pick this point rather. If I pick x comma y, guaranteed the other point exists, and I know it. Negative x, y. We should get the exact same value. We do. The y stays the same, but the x changes, which means on a graph it's easy to see. But if I had the equation in front of me and I replaced x with negative x, they spit out the exact same value in the end, the same y value. And again, we will make sure we get that jotted down. Do you guys agree with Lily that negative x, y is what we should get? Okay. The last one, origin symmetry. Anybody remember origin symmetry? So it's not just a line. That's a good thought. The line y equals x, if you're symmetric about that, you're talking about inverses and things like that, which is certainly something you did last year. A circle is good guess, not quite. These ones are easy. We're going to draw it like a cube, or if you'd rather, because everybody loves it, a tangent type looking thing. Don't stress, I'm going to draw it. It's also x cubed if you don't want to think about trig. All right, well, here's my point xy. And via symmetry, I get this lovely point over here. What's that ordered pair? Negative x, negative y. Okay. The symmetry that we see here on the graphs is nice to be able to see it on the graph, but we really don't, I think, unless you correct me, do you want to have to graph everything to solve it and see if you can make it easy? No, unless you absolutely love graphing more than anything else in math, you probably would like another approach. These are all the graphical approaches. The good news that we have is that just by having a graphical approach in front of us, if we can find a way to word what's happening with this and this, or this point and this point on any of these three graphs, then we might have a way to determine if there's symmetry in here without ever having to graph them. Which means if we did have to graph it, we just cut out half of the work if we know that there's symmetry. So as we're looking at these, let's see if we can't get these statements worked out here. We have the graphical approach. We're also going to look at the algebraic or the analytic approach. On this first one, if I replace, and I'm going to say replacing y with, what do you think we're going to replace it with? So on this one, if I plug in a y into my equation, I get this x value. What gives me the same x value? Negative what? Good. Replacing y with negative y gives equivalent expression. I'm going to use equiv expression. So we'll look at one here in a second. We'll get these statements written, and then we'll see like very specifically what this means. Okay. All right, so what about for this one? What am I going to replace with what and get the same expression? X with negative x. Now, if you guys are cool with it, can I just do it like this and say x with negative x? Instead of having to write the replacing x with negative x whole sentence again? Okay. What about this last one? Looks like I replace x with what? And y with, good. So we get an equivalent expression if we replace x and y with negative x and I'm going to use the and word rather, and negative y. And if we do that, we get an equivalent expression. Now, what does it mean to be equivalent? Like, check this out. If I say that 5 equals 5, do you guys agree with that? Okay. Is negative 5 also equal to negative 5? Those are the same equation. We just multiply both sides by negative 1. Another version of the truth in the same equation is how we can think about equivalent. So for these, I don't think I'm going to make you graph right now, but I want to, as a class or independently, we'll see what you guys think, is I want to determine the type of symmetry. And we're going to do this theoretically with the algebra approach, which I'll highlight that. All these ones are the algebra or analytic approach. We're going to determine symmetry. And all we're trying to check for is if we know that we're going to graph something and it's going to take 40 points, that sucks. And we won't ever use 40 points to graph, just so you guys know. But if the option is 40 points or spend 30 seconds doing some math to get 20 points instead, I'd much rather do the 30 seconds to save time, like for sure. And we're going to check to see how would we make that determination. So here we go. On example A for determining whether or not we have symmetry. Let's go ahead and deal with y equals, we're going to get crazy actually. Y squared plus 1 equals x. Okay. I think I'm going to just go all the way to the end. I don't think I'm just going to give you homework today. No homework tonight is kind of the plan. We'll have some time tomorrow in class to work on it. Do you guys want to start this one together? Do you want to start with your groups? What are you thinking? Okay, so I heard both. We're going to go 20 seconds, talk with your groups. I'm going to call somebody random, and you are going to push us into this problem. Make sure you are talking with your neighbors. 20 seconds, random number. You think you have an idea how you're going to start? You have an idea of how to start? Here in a second, I'm going to call on you. I would just start right with this. And we'll just see if it's the same. Like, yep, 100%. Okay, if you are struggling to check, you may be trying to do all three of them at the same time in your head, which if you're really good at mental math or comfortable with it, you may attempt that. That's reasonable. But there's three types of symmetry it could have, right? And you may know the type that it has off the top of your head, or you might not. Michaela, there's always one of three things that we can check right off the bat, though. Care to suggest that? A little bit more than just negative y. What are we going to replace with negative y? Yeah, let's replace y with negative y, and let's just see what happens. So if we're going to check to whether or not there's this lovely x-axis symmetry, well, let's just check. Instead of a y, what do we get? So negative y, if we square that and add 1 to it, allegedly that equals x. Now, I've added the negative y in. What happens when I take negative y and I square it? It becomes y squared, right? A positive y squared. So check it out. If we do y squared plus 1 equals x, and we now compare that to the original Benj, are these the same equations? Yeah, so what do you think we just discovered? If replacing y with y gave us a equivalent expression or an equivalent expression. Love it. We have some lovely x symmetry. Okay. Do we have other symmetries? And if you're not sure off the top of your head, that's okay. Sunny, we made eye contact for a second. What if I wanted to see if there was y-axis symmetry? What would I replace with what? So let's see. If we do that, I would have y squared plus 1 equals negative x. Now, when I'm trying to make these match and see, I could change this back to a positive x, but I'd have to multiply by a negative, correct? Could we ever get it to become the original again? I don't think so. I can't do the same thing to both sides and get these expressions to match. So this thing does not have y symmetry. None. It's a different equation. Well, what about origin symmetry? How would we even check it? So I'd use a negative y, and a negative x. Can you make this look like the original? I don't think so, because no matter what, you're going to have to multiply by a negative here, and it's going to break itself again. So is there origin symmetry? No, not at all. Because we have x-axis symmetry, that means for us is when we're graphing this, I might only have to plug in 3 y values, and then I get the other 3 for free because we just fold it over the x-axis. This will save time with uglier examples. For here, we're just practicing the algebra part of it. Feel okay? All right. We could start talking about a circle. We got 3 minutes. We're going to start our topic header for tomorrow. Okay. So there is no homework tonight, but we are going to add one more thing because this is where we're jumping in tomorrow. So tomorrow at the start of class, we'll need about 10 minutes, and then you guys will have time for homework, and then we might be able to start the next section. We'll see how the homework goes. But tomorrow, right at the start of class, we're going to be talking about circles. Okay, this is still in 1.2. If anybody want a washer to draw a nice circle once. Yeah, I got you. If you'd like one, please take it. We'll pass it around. And I think I can get circles on this page. Will it actually give me a circle? Oh, yeah. Well, that one's a circle, I'm pretty sure. Okay, look up there, though. Your board's tilted, yeah. But it's a circle, that's all fine. Okay, here's a circle. Give me something special about circles. Any certain parts of it. There's a radius. Okay, how do I draw a radius? From the middle to the outside. So if I do this, I have a radius. Now, I assume that there's an ordered pair, and I can even see it. I don't know what it is, but there's a point on that circle, right? It's XY. And I'm just saying it's that point. And there's a bunch of them, but it's that one. Gosh, is that center point also important? Anybody remember the kind of standard letters we use for this part? H and K. And this is my radius R. Okay, tomorrow, I'll have a bell ringer up on the board when you guys get here. Right at the start of class, while I'm doing attendance, I'm going to ask you some questions about this circle. Cool. Baller. All right. For now, if you guys are at doesn't really matter where you're at, find a place to pause. If you want to come grab your phones, you can, but don't wait by the door like cattle.